All right, let's dive into the absolute heart of every X-ray machine and ask a really basic question. How are X-rays actually made? It's a fantastic story of incredible energy, some pretty shocking inefficiency, and a wild atomic dance that happens in two totally different ways.
So everything kicks off right here. We take a whole stream of electrons, get them moving at insane speeds, and then just slam them into a metal target, which is usually made of tungsten. Now, this collision is this incredible moment where we're converting pure kinetic energy. But what that energy actually turns into, well, that's the first big surprise.
You'd think all that power is going to go into making X-rays, right? Nope, not even close. In fact, more than 99%, let me say that again, over 99% of all that energy just instantly turns into heat. The target gets ridiculously hot, but we've made almost zero X-rays so far.
That's right, less than 1%. All that work, all that energy, and less than 1% actually becomes the useful X-ray beam that we need. So the real question is, what on earth is happening inside those tungsten atoms during that tiny 1% event? Well, it turns out our electron has two different paths it can take.
Okay, let's start with path A, which is the most common one. This process has this awesome German name that honestly just perfectly describes exactly what's going on. So our little high-speed electron zips into a tungsten atom. On this path, it completely ignores all the other electrons spinning around and instead gets pulled in by the super powerful positive charge of the nucleus right at the center. This isn't a crash, it's more like a gravitational slingshot.
And that name is bremsstrahlung. It literally means braking radiation. The best way to think about it is to picture our electron as a speeding race car. As it gets close to that positive nucleus, that powerful attraction acts like a giant brake, forcing the electron to slow way down and swerve. And you know, physics tells us that energy can't just disappear. So all that kinetic energy the electron loses has to go somewhere. And poof, it's instantly shot out as an X-ray photon.
Now here's where it gets really cool. The energy of the X-ray that pops out depends entirely on how close that electron gets to the nucleus. If it's just a far pass, a wide turn, it only taps the brakes a little bit, releasing a low-energy X-ray. But if it's a close pass, if it shaves right by the nucleus, it has to slam on the brakes hard, and that releases a much, much higher energy X-ray. So if you just think about pure probability, an electron is way more likely to have a distant flyby than a super close one, right? So if you were to graph all these interactions, you'd expect to see a pretty simple straight-line graph. Tons and tons of low-energy photons, and then fewer and fewer as the energy gets higher. That's the theoretical spectrum.
But that's not what the beam we actually use looks like. And this is a great example of some really smart engineering. See, those super low-energy X-rays, they're too weak to actually get through the patient and make an image. They just get absorbed by the skin, which just adds to the radiation dose for no good reason. So the X-ray tube itself has filters built in that just absorb them, carving that straight line into the practical, bell-shaped curve that we actually need for medicine.
Okay, so that was path A, the braking radiation. Time for path B. This second method is way more direct. It's more, well, violent, and it produces a totally different kind of X-ray. This time around, our incoming electron couldn't care less about the nucleus. Instead, it's on a direct collision course. It's playing a game of atomic billiards, and it's aiming for one of the tungsten atom's own electrons, specifically one in those really deep inner shells, like the K-shell. This is no near miss. This is a direct hit. This whole thing goes down in two quick steps. First, you have the collision. Our electron comes in hot, smacks into an inner shell electron, and knocks it clean out of orbit. Second, you get the cascade. The atom immediately scrambles to fix the hole that's just been created, and in the process, it spits out an X-ray. But, and this is a big but, there's a catch. To kick that K-shell electron out, the incoming electron has to have enough power. It needs to have more energy than the binding energy that's holding that electron in place. For tungsten, that magic number is 69.5 kilo-electron volts. If the incoming electron has less energy than that, this whole interaction just doesn't happen. It's a non-starter. So once that inner electron is gone, it leaves a vacancy, a hole. The atom is now totally unstable. It's in an excited state. And you know, as the old saying goes, nature abhors a vacuum. That empty spot has to get filled, and it has to get filled now.
So, to get stable again, an electron from a higher energy outer shell immediately drops down to fill that hole. As it falls from that high energy state to the low energy state, it's got to get rid of that extra energy somehow. And how does it do it? by spitting out an X-ray photon whose energy is exactly the difference between those two shells.
So here's the key takeaway. Unlike that wide, messy, random range of energies we get from bremsstrahlung, these X-rays have very specific, predictable energy levels. And because every element has its own unique electron shell energies, these X-rays are literally a fingerprint of the target material. For our tungsten atom, we see these characteristic spikes right around 59 and 67 keV.
So we've got these two paths, right? The smooth, continuous spectrum from our breaking radiation and these sharp, discrete spikes from our collision radiation. To get the final beam that we actually use in a hospital, we've got to bring them together.
And this is what it looks like, the whole shebang. We have that broad, bell-shaped curve from bremsstrahlung, which is really the body of the beam. It makes up most of it. And then, riding right on top of that curve, you can see those sharp, powerful spikes of characteristic radiation. This combined, multi-energy beam is what gives us our diagnostic images.
So why does any of this atomic level stuff actually matter? I mean, who cares, right? Well, it matters because understanding this gives us the power to control and shape the beam, to literally tune it to create the absolute perfect image for any body part for any person.
You can think of radiographers as spectrum artists, and they have two main knobs they can turn. First is KVP. Think of that as the quality or the power of the beam, how well it can penetrate. The second is MAS, and that controls the quantity, just the sheer number of X-rays being made. By tweaking these two things, they are fine-tuning this exact spectrum for every single patient.
So let's just lock this in one last time. Bremsstrahlung, that's the interaction with the nucleus. It creates that smooth, continuous bell curve spectrum. Then you have characteristic. That's a direct collision with an inner shell electron, creating those discrete, fingerprint-like spikes. Two totally different journeys that work together to create one powerful, medically useful beam.
And at the end of the day, that's what's so amazing. This isn't just a physics lesson. It's the fundamental principle that lets doctors get the clearest possible image while giving the patient the lowest possible radiation dose. It's that perfect balance. So the next time you happen to see an X-ray, maybe you'll think about that incredible two-part atomic dance that made it all possible.